It's like a silent hole that seems to defy the laws of physics. Where does stupidity come from? Join us on a journey through this mysterious cosmos. We will travel through space, learn about new technologies, and uncover the mysteries of the void. In the larger world, the concept of nothing seems simple at first glance. Empty space, devoid of matter and energy. But in the context of life, the vacuum is more complex and interesting. Scientists say that even the densest regions of space are filled with blurry virtual particles that appear and disappear. This idea stems from the principles of quantum mechanics, according to which nothingness, or the cosmic vacuum, is not quite a void, but rather a field of infinite potential. These virtual particles, though fleeting, can have a real physical impact, hinting that even in the most desolate voids, the universe is alive. Moreover, the theory of cosmic inflation posits that our entire universe could have arisen from a fluctuation of vacuum, a kind of nothingness bursting into everything. It challenges our understanding and perception, urging us to move beyond traditional notions of emptiness or insubstantiality into a realm where nothingness is a dynamic, fundamental component of cosmology itself. According to the principles of modern physics, the concept of nothingness as complete emptiness or absolute emptiness is a philosophical rather than a scientific concept. Quantum mechanics, the fundamental theory of physics that describes the physical properties of nature at the smallest scale, suggests that nothingness in the strict sense of the word does not exist. This is because the vacuum of space, which might be considered the closest thing to nothingness, is actually teeming with energy and particles that flare up and disappear. These particle-antiparticle pairs, known as virtual particles, appear and disappear too quickly to be observed directly, but have tangible effects that physicists can measure. Physics further complicates the idea of nothingness with Heisenberg's uncertainty principle, which implies that there is a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. This principle suggests that even in what we might think of as a perfect vacuum, there are intrinsic uncertainties that prevent it from being truly nothing. In this light, physics paints a picture of a universe in which nothingness, in its purest form, is an abstract, perhaps unattainable concept that hints at the rich and complex underpinnings of our reality. The concepts of space and time play a key role in understanding the beginning of the universe, an event that is reflected in the theory known as the Big Bang. This grand event, which occurred about 14 billion years ago, marks the birth of not only all matter and energy, but also space and time as we understand them. In the singularity from which the universe emerged, all of its contents were infinitely dense and converged to a point of zero volume, which means that the concept of space as we understand it did not exist before the Big Bang. Similarly, time as a measurable progression could not have begun until the universe began to expand. The general theory of relativity, introduced by Albert Einstein, fundamentally links the fabric of space to the passage of time, suggesting that they are interwoven into a four-dimensional continuum known as space-time. This concept implies that before the Big Bang, since there was no space, there could not have been time as we perceive it. This leads to interesting and somewhat paradoxical implications for the beginning of the universe, arguing that concepts that existed before the Big Bang may not make sense in the sense in which we normally understand time. Thus, the origin of the universe defies our concepts. This indicates that the birth of the cosmos was also the birth of the very stages on which all cosmic events play out: space and time. The speed of light, which is approximately 300,000 kilometers per second, is of great importance in understanding the origin of the universe and the structure of cosmic reality. One of the most important roles of time is that it acts as the ultimate speed limit of the universe, a fundamental principle established by Albert Einstein's theory of relativity. This principle means that nothing can move faster than light, setting a boundary on how fast information and matter can travel through space. It has intriguing implications for our understanding of the size and age of the universe. Since light from distant galaxies takes billions of years to reach us, we are essentially looking backwards in time as we observe these distant corners of the universe. For example, the constant speed of light allows astronomers to map the history and structure of the universe, giving us a glimpse into the state of the cosmos shortly after the Big Bang. Moreover, the speed of light underlies the concept of the visible world, which defines the limits of the world we see. Anything beyond this limit is impossible in the space age because of the slow speed of the moon. Consequently, the speed of light not only represents the basic structure and dynamics of the universe, but also determines our understanding of its origins and becomes the cornerstone of our efforts to understand the world. Scientists around the world are trying to unravel the mysteries of the origin of the universe, and the search is as fascinating as it is challenging. One of the biggest challenges is the limitations imposed by the visible world. The speed of light, although incredibly fast, means that there is a horizon beyond which we cannot see, because light from there has not had time to reach us since the origin of the universe. This limitation means that part of the early history of the universe is inaccessible to us and forever shrouded in mystery. Another formidable challenge is the interpretation and understanding of the cosmic microwave background radiation left over from the Big Bang. Although this radiation provides a wealth of information about the early universe, deciphering its subtle fluctuations requires sophisticated technology and complex mathematical models. Cosmologists are also trying to sort out the mysterious nature of dark matter and dark energy, which make up most of the mass and energy of the universe. These invisible entities influence the evolution and structure of the universe, but avoid direct detection, making their study both intriguing and challenging. In addition, the extreme conditions of the origin of the universe, such as high energy levels inaccessible to modern particle gas pedals, mean that some aspects of the Big Bang theory and its aftermath can only be studied indirectly through astrophysical observations. The Big Bang theory, the cornerstone of modern cosmology, describes the emergence of the universe as an expansion from an infinitely dense and hot state, rather than the emergence of the universe from nothing in the philosophical sense. The theory is based on the assumption that about 14 billion years ago, the universe began expanding from a singularity, a point of zero volume and infinite density, where the laws of physics we know no longer apply. This explosive expansion filled the universe with primordial heat and energy, from which all matter eventually formed. However, the concept of nothingness preceding the Big Bang addresses deeper, unresolved questions in physics and cosmology. The singularity from which the universe is thought to have arisen derives from the general theory of relativity, which breaks down under such extreme conditions, leaving a gap in our understanding of how the transition from nothing to a singularity and then to an expanding universe could have occurred. Quantum theories of gravity, which are still in development, hint at a pre-Big Bang scenario or suggest that singularities may not exist at all within the universe, implying a different concept of nothing. The Big Bang theory elegantly explains the observed characteristics of the universe, its enormous expansion, and the cosmic microwave background radiation. However, the mystery of what preceded the singularity, or how nothingness evolved into something, remains one of the most profound mysteries underlying the understanding of our origins. The Big Bang theory, the dominant cosmological model describing the early evolution of the universe, is supported by several key pieces of evidence. First, the observed expansion of the universe provides a solid foundation for the Big Bang theory. Edwin Hubble's observation in the 1920s that galaxies are moving away from us in all directions suggests that the universe was once centered in a very dense and hot state from which it was expanding. This expansion implies that the universe had a beginning, a singularity, from which it propagated. Second, the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson, serves as a relic of the early hot and dense state of the universe. The faint microwave radiation that pervades the universe is a snapshot of the aftermath of the Big Bang, being a cosmic echo of the infancy of the universe. Third, the abundance of light elements such as hydrogen, helium, and traces of lithium predicted by the Big Bang nucleosynthesis model supports the theory. These elements were formed in the first few minutes after the Big Bang in a process called nucleosynthesis, and their observed abundance in the universe is consistent with theoretical predictions. These foundational elements, as well as the formation of the structure of the universe, including the distribution of galaxies and the cosmic web, further support the Big Bang theory, providing a comprehensive explanation for the origin of the universe and its subsequent evolution. Accidentally discovered in 1965 by Arno Penzias and Robert Wilson, the CMBR is an afterglow of the infancy of the universe, a remnant of time about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral atoms, making it transparent to radiation for the first time. This ancient light, stretched to microwave wavelengths by the expansion of the universe, provides a glimpse of the universe at this critical stage of its evolution. The uniformity of the IMBR across the sky, with only small fluctuations, provides important clues about the structure of the early universe and the distribution of matter. These minute variations in temperature, recorded by satellites such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft, are the sprouts from which galaxies and large-scale structures eventually grew. CMBR analysis also helps cosmologists determine the age, composition, and expansion rate of the universe, offering precise constraints on models of its evolution. Thus, the CMBR not only confirms the validity of the Big Bang theory, but also serves as a cosmological Rosetta Stone, deciphering the conditions of the early universe and helping us understand its origins. After the Big Bang, the universe experienced rapid expansion and cooling, initiating the formation of the first elements, an epoch known as Big Bang nucleosynthesis. In the first moments after the Big Bang, the universe was a very hot and dense plasma of quarks and gluons. In the vast and cold universe, these elementary particles combine with protons and neutrons in the first minute. In the first few minutes of life, the temperature and density of nuclear reactions increased, where protons, hydrogen nuclei, and neutrons began to combine into heavier nuclei, giving rise to the composition of the elements. A series of these nuclear fusion reactions led to the creation of light elements. First, deuterium, a type of hydrogen, is made up of protons and neutrons. Deuterium nuclei combine to form helium-3. Some deuterium and helium-3 later combine to form helium-4, the second most abundant element in the universe after hydrogen. Very little lithium and beryllium were produced in these first minutes. After the first 20 minutes, the planet will cool completely, and with the abundance of these light elements, these nuclear reactions will cease. The proportions of these first elements, about 75% hydrogen and 25% helium by mass, with traces of lithium and beryllium, match well with the predictions of Big Bang nuclear fusion models, and with what has been found in the oldest and most common. Galaxies are in distant regions. This agreement between observation and theory regarding the initial abundance of light elements provides strong evidence for the Big Bang theory and deepens our understanding of the conditions in the early universe that led to the formation of the first elements. The horizon problem in cosmology refers to the question of how regions of the universe that are far apart and should not have exchanged information because of the speed of light limit end up with the same temperature and density. This observation contradicts the expectation that, given the vast size of the universe and its age, different regions should show significant differences in these properties. Modern cosmological theories solve this mystery mainly through the concept of cosmic inflation. Cosmic inflation is a theory that suggests a period of extremely rapid expansion of the universe immediately after the Big Bang. According to this theory, a tiny fraction of a second after the universe was born, it expanded exponentially, much faster than the speed of light, for a brief period. Such a dramatic expansion would stretch out any initial irregularities or differences in temperature and density, resulting in a universe that looks remarkably uniform on large scales, as we observe today. Inflation thus solves the horizon problem by ensuring that even regions of the universe that are currently too far apart to be in causal contact arose from a small, causally connected volume in the early universe. In addition, inflation predicts the existence of very small variations in the temperature and density of the cosmic microwave background radiation, which have been observed by instruments such as the Cosmic Background Explorer, COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite. Quantum fluctuations are temporary changes in the amount of energy at a point in space, as predicted by the uncertainty principle of quantum mechanics. This principle states that measuring the position and momentum of particles involves uncertainty, leading to fluctuations that allow particles and antiparticles to spontaneously emerge from the vacuum, provided they annihilate each other quickly and do not violate the conservation of energy in time. These fleeting phenomena are not mere theoretical constructs, but have observable consequences, such as the Casimir effect, which demonstrates their physical reality. In the context of the origin of the universe, quantum fluctuations play a crucial role in theories about the very early universe, especially cosmic inflation. According to inflationary theory, the rapid expansion of the universe was caused by a scalar field known as the inflaton field. Quantum fluctuations in this region may have been stretched to macroscopic scales during inflationary expansion, giving rise to inhomogeneities that later evolved into galaxies and large-scale structures in the universe. In essence, these tiny quantum fluctuations, increasing in the scale of the cosmos, provided the initial irregularities necessary for the cohesion of matter under gravity. In addition, some theories suggest that the universe itself may have originated from quantum fluctuations in the vacuum of a pre-existing space or universe, suggesting that our entire cosmos may be the product of quantum mechanics on a grand scale. Although this idea is speculative and remains the subject of intense research and debate, it emphasizes the importance of quantum fluctuations not only in shaping the large-scale structure of the cosmos, but perhaps in its very genesis. Quantum fluctuations exemplify the intersection of quantum mechanics and cosmology, demonstrating the profound and often surprising ways in which the microscale world of particles affects the grandest scales of the universe. According to quantum theory, the concept of the origin of the universe from nothing can be understood through the framework of quantum fluctuations, which are temporal changes in energy in a region of space due to the uncertainty principle. In the realm of quantum mechanics, empty space is not really empty, but rather a seething froth of virtual particles that constantly appear and disappear. These virtual particles are pairs of particles and antiparticles that appear together briefly, diverge, and then come back together to annihilate each other, disappearing without violating the principle of conservation of energy for a short time. This phenomenon suggests a universe that could spontaneously emerge from a state of quantum vacuum, where a fluctuation of the right magnitude could trigger the creation of the universe as we know it. In this scenario, under favorable conditions, quantum fluctuation could have provided the initial energy for the Big Bang, leading to the rapid expansion and cooling that marked the beginning of our universe. The laws of quantum mechanics allow for such fluctuations, and although the origin of the universe in this way may seem improbable, it is not beyond the realm of possibility according to the current understanding of physics. Moreover, models that combine quantum mechanics and general relativity, such as the Hartley-Hawking state, suggest that time itself may have emerged from such a quantum state, smoothing the transition from nothing to a universe filled with matter and energy. These theories suggest that the early universe should not be understood as a singularity from which the universe emerged, but in terms of quantum mechanics, when the cosmos emerged from a state devoid of matter, energy, or even the very fabric of space-time in the usual sense. Quantum theory thus provides a fascinating look at how the universe could have arisen from nothing, illustrating the profound implications of quantum mechanics for our understanding of the origin of the universe. Virtual particles are a fundamental concept of quantum field theory that plays a crucial role in theories of the origin of the universe from nothing. These particles are transient fluctuations that appear and disappear in the vacuum, a quantum state perceived as empty space. Despite their ephemeral nature, virtual particles can have real, observable effects, such as the Casimir effect, which demonstrates the physical force exerted by these particles. In the context of the origin of the universe, virtual particles offer a mechanism by which the universe could have arisen from the quantum vacuum, a state of nothing in the ordinary sense. According to this view, the vacuum is not empty, but teeming with activity, with pairs of particles and antiparticles constantly arising in it and then annihilating with each other. According to some interpretations of quantum mechanics, these fluctuations can cause the birth of the universe. A particularly strong fluctuation may not annihilate immediately, but instead release energy that will initiate the Big Bang, leading to the rapid expansion of the universe from a singularity. This scheme suggests that the laws of quantum mechanics allow the universe to be created from the quantum vacuum, circumventing the traditional notion of creation from absolute nothingness. Virtual particles embody the idea that even what we think of as vacuum is filled with potential, allowing us to understand the early moments of the universe's emergence and the initial conditions that may have led to the cosmos as we observe it today. Thus, virtual particles are at the heart of modern cosmological theories, exploring the emergence of the universe from nothing and emphasizing the deep intersections between quantum mechanics and cosmology. Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, states that there is a fundamental limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. This principle has profound implications for our understanding of the beginning of the universe, especially in the context of the conditions that may have prevailed at the very moment of the Big Bang. One implication of the uncertainty principle for the beginning of the universe is that it indicates a limit to the predictability and determinism of the early state of the universe. At extremely small scales and high energies such as those that existed at the beginning of the universe, the uncertainty principle implies that energy and space-time must have been subject to fluctuations. These quantum fluctuations could lead to the spontaneous emergence of particles from nothing, potentially suggesting a mechanism by which the universe, or the energy fueling its initial expansion, could have emerged from the quantum vacuum. In addition, the uncertainty principle challenges the notion of a singularity, that is, a point of infinite density and temperature, as the starting point of the universe. Rather, it suggests that the concept of a singular beginning of spacetime may be inapplicable or meaningless because quantum fluctuations, governed by the uncertainty principle, introduce some vagueness or uncertainty into the conditions of the origin of the universe. This vagueness may hint at a pre-Big Bang state or scenarios in which traditional notions of time and space break down. Thus, the uncertainty principle not only deepens the mystery of the origin of the universe, but also provides a conceptual framework for exploring theories beyond the classical Big Bang model. By emphasizing the unpredictability and instability of the quantum state of the early universe, the uncertainty principle opens the way to a fundamentally new understanding of the birth of the cosmos. It is based on the principles of quantum mechanics. Quantum mechanics, the fundamental theory of physics that describes the physical properties of nature at the level of atoms and subatomic particles, has profoundly challenged our traditional notions of space and time, especially when it comes to understanding the origin of the universe. In classical physics, space and time are viewed as separate and absolute entities, as a stage in which events unfold. At the quantum level, however, this distinction begins to blur. One of the most striking examples is the phenomenon of quantum entanglement, where particles appear to be interconnected in such a way that the state of one of them, regardless of distance, instantaneously affects the state of the other. It involves a level of interconnection and interaction that doesn't quite fit into our classical understanding of space as simply the distance between 2 points or time as a linear progression. Moreover, quantum mechanics puts forward the idea that at the very beginning of the universe, in the Planck epoch, in the first 10 to -43 seconds after the Big Bang, the concepts of time and space as we understand them did not exist. They emerged from a singularity, a point of infinite density and temperature, where the laws of physics as we know them break down. This challenges our traditional Newtonian views, forcing us to rethink not only the nature of space and time, but also the very structure of the universe at its very beginning. Cosmic inflation is a theory that suggests a period of extremely rapid exponential expansion of the universe shortly after the Big Bang. This event is thought to have occurred within the first tiny fractions of a second of the universe's existence, more specifically, about 10 to -36 seconds after the Big Bang. The importance of global warming is that it may explain some of the world's greatest mysteries. On the one hand, this is an explanation for the marvelous harmony of the world. Despite the distance, different regions of the world are very warm and dense. Without inflation, it is difficult to explain coherence, because these regions cannot be related to each other in such a way that their properties are the same over time. In addition, the accretion theory helps explain the distribution of galaxies and the mass structure of the universe. Rapid expansion would have stretched tiny quantum fluctuations in the early universe, laying down a blueprint of sorts for the later formation of galaxies and galaxy clusters. In addition, cosmic inflation predicts a flat geometry of the universe, which is consistent with observations of the cosmic microwave background radiation. In fact, the concept of cosmic inflation is important because it provides a coherent framework for understanding the early evolution of the universe, solves several long-standing problems in cosmology, and is in close agreement with observational data. The flatness problem in cosmology refers to the question of why the universe appears so close to being geometrically flat. That is, the total energy density of the universe is very close to the critical density needed to achieve this flatness. Prior to the advent of theories of cosmic inflation, this observation presented a serious dilemma. It was natural to expect the universe to deviate significantly from flat, unless its initial conditions were tuned to an implausible degree. Cosmic inflation offers a convincing solution to the flat geometry problem by suggesting that an extremely short but exponentially rapid expansion of the universe occurred shortly after the Big Bang. During inflation, any initial curvature of space is stretched so much that the universe appears flat on scales smaller than the observed universe. This is similar to how the surface of the Earth appears flat at small distances despite its global curvature. Inflation stretches the fabric of the universe, making any existing curvature so soft that within the observable universe it is undetectable and appears flat. This expansion also means that the density of the universe would be very close to a critical density, which naturally explains why the current density of the universe is so close to this critical value for flatness. Thus, cosmic inflation elegantly solves the flat universe problem by eliminating the need to fine-tune initial conditions, making a flat universe the natural result of the inflationary process. The theory of cosmic inflation, although a novel concept, rests on a foundation of observational evidence that supports its postulates. One of the strongest pieces of evidence is observations of the cosmic microwave background, CMB radiation. The CMB is the afterglow of the Big Bang, a nearly uniform field of radiation that permeates the universe. The tiny fluctuations in CMB temperature are thought to reflect density fluctuations in the early universe that would have eventually led to the formation of galaxies and large-scale structures. These fluctuations, recorded by satellites such as the Cosmic Background Explorer, COBA, Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck spacecraft, agree very well with the patterns predicted by the theory of cosmic inflation, providing strong support for the model. See clusters. Variations in the CMB reflect these initial density variations. In essence,